We'll start now chapter 16, which is all about sound and hearing. And to start, we'll talk about sound as a wave. What is a sound wave? So sound is a longitudinal wave which travels through gas and liquids and solids. We perceive sound when those waves reach our eardrums, make our eardrums vibrate, and our brain interprets those waves. So how is sound a wave? So the first thing I'll do is I'll invite you to grab your cell phone, turn on some music, and turn it up loud. So I'm going to play a song. And as you listen to the music, put your hand on your phone. Make sure your hand covers everywhere so you can feel everything. You might have to take your case off. Um, when the music gets loud, what do you feel? Okay, I could feel it vibrating back and forth. So inside your phone is a little speaker. What I've got here is just a little speaker that I use sometimes to play stuff, but mostly I like it for physics demonstrations. If I pop the top off, and by all means try this at home, if you look at it, you see there's a little diaphragm here. So your music makes an electric signal which gets sent through a cord or through Bluetooth if it's a Bluetooth speaker. That electric signal gets transformed into a physical signal, which makes this diaphragm in your speaker vibrate back and forth. That pushes on the air molecule, and that's where our sound wave comes from. Now, if you'd like to see that speaker in action, here's a clip from The Big Bang Theory.
Okay, we're all set. Let her rip.
Hi!
Hey, check it out. It's just cornstarch and water.
They make up a non-Newtonian fluid, which is liquid, but solid under the percussive action of the speaker.
That's what makes it.
Okay, so that's something you can by all means try at home, but cover your speakers up with plastic first just to keep your speakers clean. So let's think about how the motion of that diaphragm makes a sound wave. To start, we know that our sound is traveling through air. Air is the medium, and in particular, the air molecules are the medium. So a sound wave is comprised of vibrating air molecules, and we're going to look at that next. So how does the moving speaker translate to a sound wave in air? The picture on your screen here is a video that's got a speaker, and this speaker has a diaphragm that can flex forward and backwards. And then it's in the vicinity of a bunch of air molecules. Some of them are colored red just so you can see the motion of any individual air molecule. I'm going to hit play on the simulation. What you're going to see is that the speaker will flex forward. So it'll come forwards. When it comes forwards, it's going to push the air molecules together. So it's going to compress them together. That's called a compression or condensation. Then the speaker is going to pull backwards. That's going to let the air molecules spread out. So they're going to be far apart. That's called a rarefaction. For the compressed air molecules, they're going to bump into their neighbors in front and cause those to compress. The air molecules behind will get to spread out. And then that kind of motion, that bumping into the neighbors, is going to repeat, and we'll see that the compression travels. My simulation I'm going to play is going to show that for one single tone, and then it'll show it for a continuous tone. So have a look and see if you can watch those compressions travel. So that's our single pulse, and now the continuous. Hopefully that lets you see how sound travels as a wave of compressions in air. Before we carry on talking about sound waves as longitudinal waves in the air, let's remind ourselves about longitudinal waves on a slinky. So here's a video of the slinky. I squeeze a few coils, let it go, and you see that compression travels. So in our slinky, the compressions are some coils tight together. The rarefactions are the coils spread apart. In sound waves in air, we have air molecules close together or air molecules far apart. So here I've put pictures of slinkies next to pictures of sound waves and air just to bring home that comparison. The place where the slinky is close together is above where the air molecules are close together. So that's our area. That's a condensation or a compression. So the air molecules are very close. That means they're very dense, which means it's an area with high air pressure. That's what happens when the diaphragm flexes forward and squeezes the air molecules together. When the diaphragm pulls back and the air molecules spread out, that's where the coils are far apart or the air molecules are far apart. So they're spread out. They are not dense. Why don't I say low density? And a low density will correspond to a low pressure. Now, when I say high and low pressure, it means relative to equilibrium. Okay, so the regular air pressure that's all around you. These sound waves travel as pressure waves in air, and when those pressure waves reach your ear, that's where your brain converts it into sound. One thing to notice about these pictures is that it's greatly exaggerated. The movement of the air molecules is actually very tiny, but it would be hard to see in a diagram, so it's just exaggerated here. One last thing to point out is that sound waves are sinusoidal because the source producing sounds moves with simple harmonic motion. The speed of sound in a medium depends on how the compressions travel in the medium. Speed of sound in air is something we'll discuss quite a bit, and the speed of sound in air mostly depends on the air temperature. Here's an equation that gives a good approximation of the speed of sound as a function of temperature. It's not perfect, but it's pretty close. Your book goes into a fair amount more detail, which I think is a little beyond the scope of what we want to get into, but if you're interested in it, you could certainly have a look. Now, of course, we always think about sound traveling in air, but it happens in other media as well. Here's a video from one of my new favorite movies.
Your man.
I can still hear him!
That's a clip from the movie 42 starring the late great Chadwick Boseman. So the little boy is Ed Charles, and of course, Jackie Robinson is his idol. And he's chasing him, and then he still wants to hear him, so he puts his ear to the train track, and he can still hear the train through the train track rails, even though he can't hear it in air anymore. So sound travels through solid. And this is something I used to do when I was a kid. We still used to have trains in Newfoundland back then, but before you would ever cross a train bridge, you would always put your ear down to the track to make sure no train was close by. So sound definitely travels in solids. Sound can also travel underwater. So So that's some dolphin song, which is pretty neat. You can also hear whale song. So fish and animals communicate underwater. And I guess when we were kids, we used to do that too. You would go underwater and try to talk to each other and see if you could understand it. And then the picture I have here, that's of an ultrasound. So that's when you shoot a sound wave through a human body and the reflections can show you pictures of what's inside. So some suggested activities if you would like to experiment at home. Grab a friend or a family member, someone in your home with you, and kneel as far apart on the floor as you can. So if you have a long hallway or a long room, one person knock on one end of the floor and the other person listen with your ear at the floor. Can you hear the sound come through the floor? If you can get really far apart, you might even actually be able to hear the time difference between the floor and the air. Something else you can do is make phones out of metal cans or paper cups and a piece of string. How far apart can you be and still hear the sound? So if you try any of these, please pop over to the discussion groups and tell your classmates about it. So now sound waves can have any frequency at all, but the human ear can only hear sounds between about 20 hertz and about 20,000 hertz. There's of course variation among humans, but that's about the average. Sounds with frequencies bigger than 20,000 hertz are called ultrasonic, and sounds with frequencies less than 20 hertz are called infrasonic. Ultrasonic waves, those we use in medical applications. Something that I think is really neat is that animals like elephants and whales communicate, at least in part, by infrasonic waves. It lets those waves travel over very long distances. Okay, here's a fun activity we can do. I'm going to hit play on a frequency generator. The tone might get a little bit loud, so if you're using earbuds, you might want to turn your volume down. Look at the frequency on the screen as it plays and see what frequencies can you hear. So where do you top out and where do you bottom out? Okay, I'm going to hit play now. So listen for when you can and can't hear the sound. Probably nobody hears it now. Okay, I just started to hear it. Okay, maybe most people can by now. Now we'll get higher. When do you stop hearing it? Okay, I lost it about now. And this is as high as the simulator goes. Some people might be able to hear it this far. So human hearing is really interesting. So as an example, calculate the wavelengths of the highest and lowest frequency sounds that you personally can hear. I'll do the example for me, but you go ahead and do it for you. So the lowest frequency I could hear was 24 hertz, about 24, and the highest frequency I was able to hear was about 15,200 hertz. That's pretty common for someone my age. If you're in your 20s or younger, it's probably 20,000 hertz or higher. Then kind of once you hit 40, it starts, those high frequency ranges start to fall off. So what we know about speed and frequency and wavelength is that V equals F lambda. If we want lambda, we're going to do V over F. So we need to find V. The way we calculate the speed of sound in air is we do 331 meters per second times the square root of the temperature in degrees, that's 20 degrees, plus 273 divided by 273. That gives us a speed of sound of 343 meters per second. Okay, let's use these speeds to find my wavelengths. So the wavelength of the lowest frequency sound I can hear is 343 meters per second divided by 24 hertz. And when I do that on the calculator, it gives me a wavelength of 14.3 meters. And the wavelength of the highest frequency sound I can hear is 0.022. Whoops, I went right off the screen. That's what happens when you don't look. Try that again. 0.0226 meters or 2.26 centimeters. So that's quite a range in wavelengths.